Well, this is our last section. 11.3 is all about volume and surface area. And I find this a pretty interesting section because really we nowadays have access to so much information, and so much of it is founded and based on work that previous scientists and mathematicians did and discoveries that they made. But I think there's something interesting and fun in the rediscovery of how they did some of these things. As we go through the videos in this section, we're going to be learning about how we can calculate areas, or I'm sorry, surface areas and volumes of certain figures. I rummaged the house looking for all sorts of different shapes. And I also discovered this toy my son used to have, right? It is made up of all these triangular faced figures, and they have magnets in them, and they condense. And so it has a standard volume, right? This thing, volume, is how much space something takes up, right? Figures in space. So this is going to have a constant volume no matter how I orient it, right? It's always going to be taking up the same amount of space. However, when we talk about the idea of surface area, ooh, this is one of my favorites. Surface area is the outside space. It's actually a two-dimensional, even though it's a three-dimensional figure, surface area is a two-dimensional measurement. It's how much, again, if we had to paint all of this or cover all of this. And this thing, depending on how I rearrange it, is going to change its surface area. This is full of, I have all sorts of props over here, right? I've got all sorts of games, really, because they come in interesting shaped boxes. And so we're going to look at square prisms, right? We looked at these in the previous chapter. Square on the bottom, rectangular sides. We have a cone, some holiday decorations here. Cone, circle on the bottom, and right comes to a point at the top. Got a nice cube, Rubik's Cube. We have a cylinder, another gift box, right? This is a circle on one side, circle on the other side, nice straight 90-degree bases. This is one of my favorites. It is to game hexagon, right? So there's a hexagon on this side, hexagon on the back, and the sides are perfect rectangles, right? So we can see these sides are perfect rectangles. Do we remember what this would be called? It's a hexagonal prism. So again, the top and the bottom are hexagons, and those sides are straight. I've got a sphere, right? A nice sphere. And then I'm even going to use a deck of Super Mario Brothers Uno cards to do some demonstrations as well as we go through this. So let's take a look at what we're going to be talking about in this section. Eventually, we're going to be developing some of our formulas that we're going to use. But what it's going to look like is we'll start by talking about non-standard units of volume like we've done before. Then we'll go to the standard things we use in the English imperial system and here in the United States, the metric system, and then how do we actually go about calculating these things. And so we talk about the idea of volume as how much space it takes up to fill some figure. Now, in the real world, this can be tanks, buildings, refrigerators, cars, other three-dimensional objects. If you go to buy a car, it's going to tell you the cargo space in the back of the car in terms of volume. It's going to say it has so many cubic feet, right? So that's how much cargo space your car has. We often measure cargo space, or not cargo space, volume in cubic units. Cubic units. Just like we did when we were measuring area, we measure things in squares. Now it's how do we fill some sort of object? And so we do that again in terms of cubic units. A really great thing for you to do is get something, a cube, perhaps a die, right? Or multiple die if you have these laying around, or maybe children's blocks, right? Something that's non-standard, meaning, it's not just a standard unit of measurement, but something that kids can be familiar with. The key is this is a little bit more challenging. You have to have a lot of them, and they all have to be identical, right? So that's why dice are great. If you can get just a big load of dice, that's helpful. And then grab some object, right? It doesn't matter what, grab a box like this and just see how many it takes to fill it up, right? Then you're counting the same object and saying, okay, how much is that volume? How many of these units does it take to fill one of these, right? This is then equal to, 65 of these. I'm just making that up. And so that's how you can establish that idea of volume. Another thing you can use, and we've seen this before, this tool, this is in your Blackboard, and it's this isometric drawing tool. And this, I'm going to show you a figure. So we're going to just place some of these little cubes side by side, something that looks like this, and you stack it, and then we stop, right? And so when you look at this particular figure from this perspective, a lot of students find this deceiving. If you ask how many cubes does it take to make this figure, a lot of times they will answer, let's see, 16. That's a common answer to this. How many cubes does it make? That's incorrect. What they're often doing is they're counting just how many squares they see, not how many cubes there are. This tool allows you to, again, drag and see this thing from all sides, right? Which helps that spatial reasoning. You can also do it with dice. You can tell them to stack. And we know the answer to this is 12, right? There's 6 on the top layer and then 6 more on the bottom layer. That would indicate the volume of this. Once you've developed the idea of measuring volume, particularly in non-standard units, then you can go to the standardized units of volume, and we'll start with the ones that we have in our English system. These should be familiar to you, at least the names, because we've already discussed things like inches and feet and yards. And so these are now cubic inches and cubic feet and cubic yards. And so as you can see, a cubic inch is a cube that measures exactly 1 inch on all sides. A cubic foot, which is 12 inches on each side, would measure a foot by a foot by a foot. And then a yard is 3 feet. And so a cubic yard would be 3 feet or 1 yard on each side as well. If you can then have discussions about what are the sorts of things you could measure in cubic inches or cubic feet or cubic yards. As we said before, maybe you measure like the space inside your microwave in cubic inches. Or as I already talked about, the cargo space inside the back of your vehicle in cubic feet. If you've ever done landscaping and had to order dirt or mulch or sand to be delivered, they call it yards. You buy in yards. What they really mean is cubic yards. And so those are the things you might purchase with those. It's also important to be able to understand how we would go from one of these to the other. How many cubic inches belong in, say, a cubic foot? So let's take a look at a picture of that. So here is a picture. And just take a moment to analyze that. What you'll notice is this is a picture of a cube, and each side of our cube is 12 inches, which also means each side of our cube is 1 foot. And so we can say that this cube is 1 cubic foot. But if we want to express that same volume in cubic inches, we would count how many cubic inches are on that bottom layer, which is 12 this way and 12 this way. We know 12 times 12 is 144. So there's 144 cubes on that bottom layer. And then what we're going to do is we're going to stack layers of 144. So you'd have 144 on the bottom layer, 144 on the next layer, 144 on the next layer, and so on. And you would have 1, 2, 3, 4, 5, 6, 7, 8, 12 layers, each with 144 in them. 144 times 12 layers is 1,728. So to fill this box, you would need 1,728 of these little cubes. And each one of those is a cubic inch. And earlier I wrote a 2 there, and I see I should have written a 3. I said cubic and I wrote a 2. We use the exponent of 3 to demonstrate cubic measurements. So 1 cubic foot is equal to 1,728 cubic inches. So my next question to you is, can you calculate how many cubic feet would it take to fill up a cubic yard? Take a moment to do that. These are a little more challenging to draw. I can draw my cube. And if we know that this is again, this is a cubic yard, let's say, which means each side measures 1 yard by 1 yard by 1 yard. Remember, that's something you might purchase, again, dirt or mulch in something like this. Well, each yard is the same as 3 feet. 3 feet. 3 feet. So in the bottom corner of this, what you might have is a cubic foot drawn, right? So this is 1 cubic foot. It would measure 1 foot on each side. So how many of these would it take to fill up this entire cubic yard? Well, you would have 3 this way and 3 this way. So you'd have a layer of 9 on the bottom. 3 times 3 is equal to 9. And then you would have 3 layers of 9. 9 times 3 is 27. So 1 cubic yard is the same as 27 cubic feet. And here's a little chart that summarizes that information that we just went through. Again, a cubic foot is 1,728 cubic inches, and a cubic yard is 27 cubic feet. We can also measure volume in the metric system. And just like we did before, there are somewhat standard or common measurements used in the metric system. Here are a couple of those examples. Now, a cubic millimeter is going to be very, very small, right? And so these are certainly not drawn to scale. But a cubic millimeter would be 1 millimeter on each side. A cubic centimeter is 1 centimeter on each side. And a cubic meter is a meter on each side. This one's a little easier for us to picture, right? Imagine sticking your arm out to the side, about the distance that you can see to the end of your fingertips. And now imagine a box with that dimension up, down, left, and right. That's about the size of a cubic meter. A cubic centimeter, right, is probably a little smaller than one of those die that I was showing you earlier. And so it's also important to understand how many it takes of one of these to make up the next one. And having a good understanding of the metric system is important. And so let's first talk about how many cubic centimeters. So this is 1 cubic centimeter. How many of these would fit into a cubic meter? Take a moment and see if you can answer that question. Well, that's already started to be sketched out for you here. Hopefully you remember that 1 meter is equal to 100 centimeters. 1 meter is 100 centimeters. And so each of the sides of this figure would also measure 100 centimeters. 100 centimeters. And if we can imagine, kind of like we did earlier with the inches, imagine 100 centimeters stacked this way, little cubes, and then 100 centimeters, cubic centimeters stacked that way, and then filling up this entire base. What's 100 times 100. 10,000. It would take 10,000 cubic centimeters to fill up just one layer of a cubic meter. And then you would need 100 levels of those. So that would get multiplied by 100 again. And what you end up with is 1 million. It would take 1,000,000 cubic centimeters to fill up a cubic meter. We can summarize some of these conversions or relationships with this chart. We just did this one. 1 cubic meter has 1,000,000 cubic centimeters. 1 cubic centimeter is 1,000 cubic millimeters. Why is that? Because each centimeter is made up of 10 millimeters. So this would be 10 millimeters by 10 millimeters by 10 millimeters. 10 times 10 times 10 is 1,000. So just to look at some application problems of this, let's ask these questions. And the first one is about the volume of a refrigerator. A freezer has a capacity of 28 cubic feet. So how many cubic inches is that? The next one says a small box holds 230 cubic centimeters. How many cubic millimeters will it hold? And then the next question is, which of these calculations is easier to do mentally? Take a moment and see if you can work through those problems on your own. So the first one is involves some of those things we looked at earlier. A freezer has the capacity of 28 cubic feet. And we want to know how many cubic inches is that? Well, again, a cubic foot is much bigger than a cubic inch. So just like we did when we were dealing with area conversions in the previous section, if I say this is 1 cubic foot, do you recall that this is 1,728 cubic inches? Remember that from up here? 1 cubic foot is 1,728 cubic inches. If we have 28 cubic feet, it means it's 28 of these things. This thing, we're going to have 28 of them, which means we need to take that number, 1,728, and multiply it by 28. When we do that, we are going to get a total of, pretty big number, 48,384 cubic inches. So a pretty big number. The second question was, a small box will hold 230 cubic centimeters. So again, imagine we have a small box. And we need to say 230 cubic centimeters is how many cubic millimeters? So let's just say this box is going to represent 1 cubic centimeter. How many cubic millimeters is 1 cubic centimeter? Remember from above, it was 1,000 cubic millimeters. So every cubic centimeter contains 1,000 cubic millimeters. We have 230 cubic centimeters. So we have this times 230. Well, 230 times 1,000 is 230,000. Which then leads us to that third question, which is easier to do mentally. The second one. Why is that? Because when we're multiplying by 1,000, we are essentially just adding 3 zeros to the end of our number. There is the benefit again of that metric system. Everything is based on powers of 10, so the calculations are much easier to do. So another concept we need to talk about, sort of the generalized concept, is the concept of surface area. And I mentioned this a little bit earlier. And so surface area is how much space does it take to cover the outside of an object. Let me show you this. So I have my son's, one of his Rubik's cubes, right? He can solve this Rubik's cube. So this thing, right, this is a 4x4 Rubik's cube. The traditional is a 3x3. And so what you'll see here is that this has 4 rows of 4, right? So it's stacked 4 rows of 4. And when we're looking at volume is how much space does this take up? So we'd be counting cubes. But surface area is how much space is each side of this. And so we can see that this is 4 across and 4 down, which is a total of 16 of these little squares on this side. Well, there's also 16 squares on this side, and this side, and this side, and 16 here, and 16 here. So every side of this has 16 square, we'll say these are centimeters, 16 square centimeters, and there are 6 sides. So to calculate the surface area, we basically just add the surface area of each individual side. So this would have whatever 16 times 6 is. And so that's the idea of surface area. What does it take to cover the figure? Often we will investigate something that looks like this, where we can only see that much of it. And so see if you can find out, let's assume that each one of these is, lengths from here to here is 1 centimeter, which means each square is a square centimeter. See if you can find the surface area of this figure that we see right here. This takes a little bit of investigation and a little bit of thinking because it takes spatial reasoning. You almost have to be able to imagine rotating this thing around in your mind, like I did with that isometric app tool earlier. And so you've got to consider all 6 sides. So the top has 1, 2, 3, 4, 5, 6, 7, 8, 9. So the top has 9, and these are my square centimeters. Well, the bottom is going to be identical to the top, but we just can't see it. So the bottom also has 9. This side has 1, 2, 3, 4, 5, 6. So we'll call that the left. So the left has 6, and the back of, we'll call this the right side, which we can't even see back over here, would be identical to the left. We'll call this the front, 1, 2, 3, 4, 5, 6. The front also has 6, which means the back side, again, which we can't see, also has 6. What you'll notice here is that opposite sides are always going to be identical. So if we have 2 times 9, which is 18, 2 times 6, which is 12, 2 times 6, which is another 12, and we add those together, we get a total of 42 square centimeters. So that's one way that you can calculate surface area. Now, one of the things that we talked about when we were doing, or in the previous video with areas and perimeters, was that there's not always a relationship between the two. The same is true with volume and surface area. And so I'm going to show you another picture of a figure. This actually has the same exact volume as the previous shape. It has 18 cubic centimeters. There are 18 cubes here and 18 cubes here. But now calculate the surface area of this figure. What you might notice, again, is that if you look at the top, it is a 3x6. So this top part has 18 square centimeters. This side has 1, 2, 3, 4, 5, 6, and this side has 3. We also know that the opposite sides are the same. So we have 2 18s, we have 2 6s, and we have 2 3s. That makes 36 on the top and bottom, 12 on the left and right. And I wrote a 3. I don't know why I wrote a 3. That should be a 2 right there, which means we have 6 total on the front and the back. Add those up, and I believe we get 54 square centimeters in this figure compared to 42 in the previous. So just like when we were dealing with perimeters and areas, there's not always a relationship or a correlation there. There is, depending on how it's arranged, you can have a different surface area for things that have the exact same volume.